In this video, we'll look at some famous transformers. The basic structure of all these models is not new, and we'll focus primarily on the details of their architectures and the details of the way they were trained and what they were trained for. We'll start with the original transformer, the model that coined the name transformer. Then we'll look at BERT, and then we'll look at the GPT family of models, in particular GPT-2 and GPT-3. The original transformer looked like this. So this is quite a complicated and convoluted architecture. But don't worry, things will only get simpler from here on. And this model was introduced in a paper called Attention is All You Need from 2017. And the main breakthrough here was not the introduction of an attention mechanism. Attention mechanisms had already existed for quite a long time. The real breakthrough here was that you could use attention mechanisms in isolation without recurrent neural networks or convolutional neural networks in the mix. You could build a highly performant model purely on the attention mechanism alone. Hence the title, Attention is All You Need. The model was a machine translation model, so it was structured in an encoder-decoder configuration, which was popular at the time for machine translation models. And this is the teacher forcing method that we also saw in lecture 5. Essentially, the encoder consists of a stack of normal self-attention blocks without masking. So these are blocks that have access to the whole sequence. They take in the English language sentence and produce a hidden representation in green. And then we have an autoregressive model as a decoder to which this hidden representation is fed through the side as the key and query of a second attention mechanism. So on the right in the decoder model, the transformer block consists first of a masked self-attention and then what is called a source attention, where the values are made up of the output of the self-attention and the key and query are made up of the green sequence that is based on the English input sentence. And once this model is trained, the French sentence can be sampled sequentially in this autoregressive fashion. The size of the model was relatively modest, because the point of this paper was not so much to show what a large transformer model can do, but that if you stick purely to self-attention layers, you can train a state-of-the-art model with relatively modest compute in a short time. To be specific, this model was trained for 3.5 days on 8 GPUs. The next step in transformer models was to increase the size of the model and to simplify its structure. That step was mainly taken by the model BERT, which functioned as a kind of spiritual successor to the Elmo model we saw earlier, which is to say it was built on a principle of large unsupervised pre-training and supervised fine-tuning to specific tasks. It consists very simply of a single stack of non-causal transformer blocks. It uses position embeddings rather than position encodings, and it contains 24 blocks and 340 million parameters in total. Now with BERT, there are a few interesting additional features to look at. And the first is the way the input sequence is tokenized. So far we've looked at word level tokenization, where we try to split the input sequence into its constituent words as well as possible. This results in a very large output layer because we end up invariably with a very large vocabulary. And it's not flexible to typos and to uncommon words because most likely these will be outside our vocabulary and we have to replace these with a special token that signifies that this is an unknown word. Instead, we can do character level tokenization. That allows us to represent any word we encounter. But the problem then is that we end up with very long sequences and we spend a lot of computation learning known words or sequences of tokens for which we know that they form a unit already. So there's really not much point in learning this from the data. A middle ground between these two approaches is subword tokenization, which allows us to define a vocabulary of around 30,000 words and still have every sequence that we can encounter be representable as an input sequence to the network. And what it looks like is something like what you see on the right here, where the sentence "jet makers feud over seat width with big orders at stake" is broken up not always into its constituent words, but for some relatively rare words like jet and feud is broken up into subword tokens. Whereas for more common words like makers, these become tokens in their own right. There are two common approaches for this: byte pair tokenization and word piece tokenization. So let's start with byte pair tokenization. The principle is very simply to start with a character level sequence and to merge the pair of characters with the highest frequency in the data. This is called a bigram. So in the first line we see the man commands the plan, and we'll take that as our entire data set broken up into characters. And the most frequent bigram in this sentence is the sequence AN. So we take all the occurrences of the sequence AN and we replace it by a new token representing those two characters. And then we repeat the process after we've introduced this new token. So afterwards, the token man, the combination of the base character M and this new character AN, becomes our most frequent bigram, and so we extract that and replace it with a new token as well. And note that only 2 of the 3 occurrences of AN are replaced by this new token, because the last one is in the word plan. And word piece tokenization works very similarly, except that it looks not just at the bigram with the highest frequency, but it looks at the bigram which most increases the likelihood of the data. And that's assuming that the data is drawn character by character according to the relative frequencies in the data. The training data for BERT was primarily from English Wikipedia. So they took over 2 billion words from English Wikipedia. And to introduce a little bit of variety of language, they also added 800 million words from what is known as the books corpus, which is a corpus of 11,000 copyright-free books scraped from the internet. In pre-training, the input sequences were not restricted to be sentences. They were simply sequences of L-contiguous words cut from anywhere in the corpus. So most of these contained multiple sentences, and the boundaries of the sequence were probably somewhere in the middle of a particular sentence. This means that during training we always have a fixed sequence length, which makes training much more predictable. But because it is a sequence-to-sequence model, during fine-tuning, the model can still scale to sequences of different lengths. BERT was trained on 2 tasks. The first is the masking task, also known as the bidirectional language model training, where we simply take an input sentence and make the target that same sentence, except that in the input some of the words are corrupted. Some are corrupted by replacing them by a special mask token, and others are corrupted by replacing them with a random word from the vocabulary. And others are corrupted by replacing them with a random word from the vocabulary. We then compute the loss only on these corrupted or masked tokens, but since BERT doesn't know which ones we've corrupted, it needs to produce predictions for all of the words in the sentence. And we train on randomly sampled sequences of 512 tokens. And the main purpose of this task is to produce token-level representations, output representations that represent the individual tokens in the input sentence. The second task, the classification task, is designed to force BERT to also create representations for the whole sentence. And to do this, we introduce first a special CLS token, which is placed at the start of every input sequence, and we look only at the output label of that token. And as input, we sample either 2 sequences from different parts of the corpus, or 2 sequences directly following each other in the corpus. These are concatenated with a separator token in the middle, and BERT's task is to predict whether these are contiguous sentences or sentences from different parts of the corpus. And because we classify purely based on the value of this CLS token in the output, ignoring all the other tokens, this forces BERT to put a global representation of the whole sequence into the CLS token. And it turned out that this was enough to reach state-of-the-art performance for a large number of natural language processing tasks, better even than the ELMO model, which was introduced a year earlier. Finally, we'll look at the GPT family of models. The first GPT was introduced with very similar purpose as BERT, to serve as this kind of unsupervised pre-trained model in the vein of ELMO. But by the second GPT model, which was trained in much the same way and only scaled up, its purpose began to shift a little bit to more generation of text. So we'll start with GPT-2, which is an autoregressive language model, as we've seen before. So it's a model that is very simply trained on a particular input sequence, and its target is predicting the next token at each point in the sequence. It consists very simply of a single stack of causal transformer blocks, so transformer blocks with masked self-attentions. It uses position embeddings like BERT, and it has a slightly lower dimensionality than BERT, but more transformer blocks and a larger sequence size. It consists of 1.5 billion parameters in total, and it was trained in about 7 days on 256 TPU cores. A large part of the success of GPT-2 comes from the quality of its data, which was the web text dataset. This is a web crawl of what the authors call high-quality web content. And the way they determined high quality was to look at how many upvotes a particular link received on a social media platform. And in particular, they used the social media platform Reddit, which assigns a value called karma to links. So they looked at links with a particular minimum amount of karma, which gave them a collection of 45 million links. They downloaded the resulting links, pre-processed them, and deduplicated them, resulting in 8 million documents and about 40 gigabytes of text. Note here that Wikipedia was explicitly left out of these links, because Wikipedia is often included in evaluation datasets, and they didn't want to include the language from the evaluation dataset in the training data. Note also that this doesn't mean that GPT-2 is trained on the content of Reddit, which is a common misconception heard in criticism of GPT-2. It's only trained on general websites that are linked to from Reddit. Like with BERT, all inputs are sequences of L-contiguous words from the corpus, not necessarily sentences. And here we use byte pair tokenization. One thing to note is that if we were to use byte pair tokenization on Unicode text, we would have 16-bit characters, which gives us around 60,000 base characters before we even start merging. So to avoid this situation, what the authors did was to break up every Unicode character into 2 bytes, and to take this sequence of bytes as the basic sequence on which they start merging. And this gave them 478 base characters, which after 40,000 merges led to a vocabulary size of 40,478. And the main breakthrough of GPT-2 was the quality of the text that was generated from it by sequential sampling. So here's a famous example, where at the top we see a human-written system prompt, and below where the italics end and the Roman characters start, we see how the model completed this text. And we've seen some pretty interesting examples of generated text already in the context of LSTMs, but what the LSTMs couldn't do, and what GPT-2 can do, is to produce text with long-range coherence. So for instance, when we generated convincing-looking Shakespeare from an LSTM, we saw a style of language that looked very natural, but the character names shifted from one bit of text to the next. So what these LSTMs never learned was that in a particular play, the same character name should occur over and over again. That's what we call long-term coherence. As we generate a long bit of text, it should be about the same topic, it should contain the same characters, the same names, and so on. And that kind of coherence doesn't emerge from an LSTM language model. But as we see here, it does emerge if we sample from GPT-2. The prompt sets up a couple of facts. There are unicorns, the unicorns speak English, and the location is the Andes Mountains. And all of these facts keep coming back throughout the news article. The model imagines a scientist called Dr. Jorge Perez, which is a suitable name for a story set in the Andes. And the unicorns also keep coming back throughout the story. And you can play around with this model for yourself at talk2transformer.com, where you can try this prompt, a number of other prompts, and you can also type your own prompts. And because of this quality of generated natural language, GPT-2 was probably the first neural network model to receive widespread mainstream media coverage. The reason for this was that when the OpenAI researchers saw the quality of text that GPT-2 produced, they decided not to release the model immediately. And the main reasoning behind this was that with this kind of model, a large-scale social media fake news campaign might be suddenly within the grasp of a single individual with a reasonable budget, rather than only within the grasp of large institutions. So OpenAI followed a responsible release schedule. Over the next 6 months after the paper was published, they first released the model only to researchers specifically working on the topic of AI safety, and then slowly increased the size of the model that they released to the general public. Meanwhile, because clearly the limit of what could be achieved by transformer models clearly hadn't been reached yet, they began training GPT-3, which follows the very same basic structure as GPT-2 and simply trains on more data and is a much bigger model. So it's still a single stack of causal transformer blocks with all the same details as GPT-2, but now we have 96 blocks with 96 heads each and a whopping 12,000 input dimension. And they've also doubled the sequence size that the model is capable of consuming. This led to a value of 175 billion parameters in total, which is by far the biggest neural network trained and published at the moment. It was trained on a purpose-built compute cluster containing 10,000 GPUs, and the best estimate is that this took around 12 days and cost about $4 to $5 million for a single training run. To train a model this big, the authors needed a large dataset. Luckily, the internet contains as much data as we could possibly want. The main problem is to extract the high-quality data. This was done by first training a special classifier to tell text that came from the original web text corpus of GPT-2 from a randomly selected bit of the common crawl data, and then applying this classifier on the entire common crawl data to select articles that look like web text. That is, that look like high quality language. And this is done noisily so that occasionally some out of distribution examples slip into the data. The authors also applied a fuzzy deduplication so that the finally extracted data didn't contain too many duplicate articles. And then they added a number of additional known high quality datasets like an extended version of web text, Wikipedia, and 2 books corpora based on published books that are posted online. Unsurprisingly, this model took a long time to train and required a lot of compute to train. So here's a comparison with some other models, some of which we've seen. In the green there's BERT large, which is one of the models we started with. And note here especially the logarithmic scale on the vertical axis. So even though the bar is only 4 times as high, that means there's 4 orders of magnitude in between BERT large and the largest version of GPT-3. Like its predecessor, GPT-3 was very good at generating natural-looking language, and the language was so good that for a large proportion of its output, human annotators had considerable difficulty telling a GPT-3 generated article from a human written article. But the really interesting thing that the authors found about GPT-3 when they finished training it was that it could do few-shot learning purely by prompting. So few-shot learning is a practice of pre-training a model on one domain, showing it a few examples of a new domain, and then attempting to make it learn that task in that new domain. And usually this is done by a small amount of retraining. So we pre-train on our source domain and we retrain a little bit on these small number of examples from this second domain. And what we see here is that GPT-3 can do this few-shot learning not by retraining. So the model parameters stay as they are never retrained, there are no gradient updates. The few-shot learning is purely done by prompting. So at the start of the sequence, we add a few examples of the kind of thing we're expecting, and then we add half an example that we want completed, and then we let the model complete it. So here the task is to take a poor English input and turn it into a good English input, and we simply feed the model with a prompt, which is shown in gray here, of a couple of poor English inputs followed by their corrected versions. And then the prompt ends with a poor English input, after which we expect the model to reply with a good English input, correcting the grammar in the sentence. And what we see is that GPT-2 is perfectly capable of doing this after a few examples. For instance, here it corrects the sentence, I'd be more than happy to work with you in another project, to I'd be more than happy to work with you on another project. Here's another example. In this task, the idea is to take a non-existent word, read its definition, and then use it in a sentence. So first, we show the model an example of what we're looking for. A watpu is a small furry animal. An example of a sentence that uses the word watpu is, and then an example of a sentence that uses that word. And then in the next part of the prompt, we do the same thing, but we stop after an example of a sentence that uses is, and then expect the model to produce a sentence of that type. And what we see here is that the model produces reasonable sentences that follow the given definition. We've talked before in the context of Word2Vec about model bias, which is an important problem. Our training data in general reflects the biases that exist in the world. So a model trained on those biases at best will reflect those biases as well, and at worst will amplify those biases. And GPT-3, as the authors show, is no exception. The biases that exist in the world are there in the model. And as we said in lecture 4, even if these biases are accurate predictions given the data, that doesn't mean that they're safe to use to produce actions. Any products built on this technology should be carefully designed so that they don't amplify these biases once released into production. And for a good example of this, look back to the Google Translate example shown in the Elmo and Word2Vec video of lecture 5. As you might expect, GPT-3 led to a lot of heated discussions about what all these results meant and how intelligent GPT-3 really is. You can read these for yourself. We just would like to give you the following tips in analyzing these discussions. And the first is that it's very important to distinguish between the model GPT-3 and GPT-3 with a well-written prompt. Because if we're simply giving GPT-3 a bit of text and asking it to complete it, basically the model doesn't have enough information to understand what it is we want it to do. And most problems cannot be solved in this zero-shot setting. We need to communicate to GPT-3 what our assumptions are, and that is done through the prompt. So really, if you want to evaluate the performance of GPT-3, if you want to evaluate whether GPT-3 can do a certain kind of reasoning, what you need to do is give it a few examples of the kind of reasoning you expect it to do, and then give it a prompt. And then give it an incomplete example to see if it completes it correctly. So usually the relevant problem is not can GPT-3 solve the problem, but how much of a prompt does GPT-3 need to solve the problem. A lot has been written about GPT-3, but a lot of it is highly dubious. So if you want to interpret these things correctly, we recommend reading the paper before you start reading the editorials. So that's a small sample of the most important transformer models out there. There are many more, like T5, RoBERTa, and ExcelNet, but they all build on the same principles, and you can easily find out about these for yourself. In the last video of this lecture, we'll look at some of the existing problems with transformer models and some of the tricks that are being developed to solve them.